Okay, I'm going to explain this worksheet that's all about dilution. So you can see up here at the top there's a formula that we're going to use. M1V1 equals M2V2. What this has to do with is, what we're saying is when something's diluted, the number of moles of whatever's dissolved, the number of moles of solute is the same. And so what this comes from is a rearrangement of the formula M. The molarity equals the number of moles over the volume, number of moles of solute over the volume of solution. So if we just multiply both sides by V, we get M times V equals N. And so what that's saying, again, is that the number of moles is going to stay constant when you dilute something. And so what we get is M1V1 equals M2V2. So continuing on down here, this is the first example. It says, you dilute 175 milliliters of a 1.6 molar solution of LiCl to 1 liter, determine the new concentration. And so in this one, it's important that we look at the units here. For volume, since volume is on both sides, you can actually have it in milliliters or liters, but it's important that you're consistent about your units. And so on one side, we're given milliliters, and on the other side, we're given liters. And so what I'm going to do is I'm just going to say 1 liter is the same as 1,000 milliliters. Okay, and so then I just plug it into the M1V1 equation. M1V1 equals M2V2. So 1.6 times the initial volume, which is 175, equals M2 times 1,000. Solve for M2 there, and you get that the final molarity, or the final concentration, equals 0.28 molar. For problem number 2, this one says you need to make a diluted 10 liters of 1.2 molar KNO3. What molarity would the original potassium nitrate solution need to be if you were to use 2.5 liters of it? So we've got an original 2.5 liters of concentrated solution, and we're going to dilute it down to 10 liters. And so this one's kind of backwards a little bit. It gives you the final information first, and we're trying to figure out what the original molarity is. So M1 is what we're looking for there. If you got these switched, in terms of the sides, it doesn't really matter as long as you're keeping the initial conditions together and the final conditions together. But we're going to say M1 is what we're looking for. The original volume is 2.5 liters. All right, and what we're making with that is going to be a concentration of 1.2 molar, and there are 10 liters of that. Oops, 10 liters. And so going through doing the math on that, you get that M1 equals 4.8 molar. So that is the original concentration. Problem number 3. You're given a solution of 5.0 molar CaCl2. You want to make 500 milliliters of 3 molar solution. What volume of the original solution do you use? So now we're looking for volume of the original solution. And so we've got M1V1, so 5.0 is the original concentration. V1, the original volume, is what we're looking for, equals M2V2, so that's 3.0 times 500. Right? What we get out of that is that V1, the original volume, equals 300 milliliters. Problem number 4, we've got a situation here. We've got a concentrated solution. I want to know how much water we need to add to dilute it to a specific concentration. And so this one says, careful that asking how much water you're adding is not the same as asking what the final volume is. And so we'll do this problem very similar to what we did before. We say M1V1 equals M2V2. M1V1, we've got, it's 5 molar, and times 1 liter equals M2V2. We want it to be 1 molar in the end, and then we're going to try and figure out what V2 is. You solve that, you get V2 equals 5 liters. All right, but this asks how much water you need to add. And so we originally had 1 liter. The final volume is 5 liters. So what this means is that you need to add 4 liters. Okay, and now this final problem. What it says is that we're given 2 different solutions, but both of them have the wrong concentration of H2SO4. And so what we're trying to do is make a new solution that has a concentration of 2 molar, even though we're starting with solutions that have 4 molar and 1.0 molar. What this is going to keep in mind is, remember that I said the number of moles from the beginning of before you mix them is going to be the same as the number of moles in the end. All you're doing is mixing things together. So the number of moles of dissolved particles, number of moles of solute are going to stay the same. So I know N1 plus N2, the number of moles that are in both of the original solutions that we're mixing, ends up equaling the combined number of moles after we mix them together. And then, taking advantage of the fact that we've got the number of moles equal to molarity times volume, we get M1V1 plus M2V2 equals M3V3. So now we just plug things in. We've got, for the first one, it's got a molarity of 4. The volume, we don't know what that is, so I'll just call it V1. Plus, the molarity of the second one is 1. I'll come back to the volume there in just a second here, actually. We know the molarity of the final one that we want is 2, and we know the final volume, I said we wanted to make 100 milliliters total. Now, if we're trying to make 100 milliliters, this is where the really tricky part comes in. Whatever our volume 1 is, the remainder is going to be our volume 2. And so instead of saying 1 times volume 2, what I'm going to say is 1 times 100 minus volume 1, because that will give us what volume 2 is. And now we only have one variable in there. So then we go through and we can simplify that. I get 4V1 minus V1 plus 100 equals 200. And then that simplifies even further down into 3V1 equals 100. And then you get V1 equals, it's going to be 100 divided by 3, or 33.3 milliliters, which means the remainder is V2. That's going to equal 66.7 milliliters. And this is, just to keep in mind, the V1 was the 4 molar solution, and V2 was talking about the 1 molar solution. So that's how we would mix them if we wanted to make the correct concentration there.